Hi everyone. So this is Project Pac-Man Capture the Flag and our team in Victex Gaming. So now we are just explaining what we are approaching our method to implement this project. So in the offense methods, we implement two methods. First one is the Q-learning and another is the Monte Carlo tree search.
The first one we implemented is the Q-learning. Why we implement this? Because we just learn the reinforcement learning. We wanna enhance our understanding of this Q-learning. But actually, in the process, we found it is very hard to implement Q-learning since it's very hard to define the features, and we found some features may be conflicts and lead to our performance very bad. And also the reward point is like very sparse, so the agent can't very get the learning when we running the game. So we consider lots of situations, and we find a possible improvement is that we can divide this game into two parts. One is to searching the dose when we have no carrying any dose, and then we consider if we have the dose, we returning the game. So we separate the game into two different size, and we define two different width features, and we can learn the different widths from different features. But we are actually running out of time, so we just decided to use another method called Monte Carlo trees.
Another method we're using is the Monte Carlo tree search. First of all, the Monte Carlo tree search has the advantage on just distribute in more steps, which means that we can predict like several steps, for example, 10 steps further to the result. And for more explanation, here is our model. First of all, we are in the current state, which means the Pac-Man in a certain position, and it will explore expanding the nodes that he can move to. For example, when he moved to the step 1, and then he calculate the value to move to another state, to state 2. When he get to the state 2, and he do the random simulation, it randomly simulate through about several steps. In here, we choose to 6. It means he moves 6 steps randomly and calculate each step's values and sums up. And then he do this again and again about 5 times and get the average values to propagate back to store in here and updating. So always we're getting the best scored to expand each node to get to back propagate to the best score. This move is what his decision makes.
So this is our Q-learning agent. You can look at that. Our agent is like good at dodge the ghost and eating dots, and it also will eat the capture and to attack the ghost. But it will confused at one point because at this point we already carries a lot of carries and we decide to return. But actually the return features is conflict with currently eating dots features. So it will lead to our agent to learning to become very confused in this time. So what we have to do in next improvement is separate these features into different into a dynamic version. But we are running out of time, so we decided to use Monte Carlo tree to perform a better solution.
So here's a demo on MCT trees. So the dark blue one, you see this one is our offensive agent. So first of all, he found out the closest foot and eat it. And then he see the enemy and going back, step forward, a step back. And then he has one score carry, but under this condition, he will decide to going back for scoring. So, and he did it. And after he goes back in, but now he's not carrying any foot, so it will be careless about going back. So he will find out the next foot positions. And then he found it. And also it found the capsule which gets more values. And then he did this move is like very predictable. Right? It's like in a prediction to finish this operation. This is the advantage by using an MCT tree. You can see, and now he's carrying a certain amount of the food, and then he decided to go back to full score. So by MCT tree, it's more easy to handle the scoring issue.